Hello, Sol Solar here. So this is lecture 2 in my short lecture course on the physics of consciousness, the principles of the physics of consciousness as I've written them, and how to use them to make a scientific theory of consciousness. Lecture 2. So in this second lecture, we are going to talk about quantum mechanics. As I said in the introduction, quantum mechanics and consciousness are twin mysteries. The solution of one immediately solves the other. Okay, before we start, let's very, very briefly recap the first, the major results of the first lecture. We changed the fundamental postulate of consciousness. So all emergent theories are based on the idea that the energy created in the Big Bang the basic energy of this universe possessed and still possesses no intrinsic consciousness. Consciousness is not a fundamental property of energy in emergent theories. And then you have non-conscious energy. Out of that energy you get non-conscious particles. They form non-conscious atoms, non-conscious molecules, cells, etc. At some point these cells can get specially configured such that into brain cells, for example, and then consciousness switches on around these special configurations. Those are emergent theories. And we said that for 100 years they've proved totally, that assumption has proved totally fruitless as the basis for a scientific theory of consciousness. So we've changed it, and we're saying that consciousness is an intrinsic property of all energy. All energy within itself is conscious. And the conscious experience it's having at any given time depends on its particular form or configuration. And one thing you can know for a fact is that when you arrange conscious energy and particles into your physical form, it gives rise to your conscious experience, which you're experiencing now. And of course, you're physically connected to your local environment, and these physical processes cause changes in your consciousness as well. So we've changed the fundamental postulate of consciousness. So our theory is based on the idea that all energy is intrinsically conscious, which makes sense because we're made of nothing but this energy and we're intrinsically conscious. Okay, those I think were the major points of the first lecture. So now we move on to and that solves the hard problem of consciousness. You're conscious because everything you're made of is conscious. So we've solved the first lecture, we solved the hard problem of consciousness. Now we solve quantum mechanics. And this basically puts my theory beyond reasonable doubt, because for 100 years, people have been searching for a simple, logical, intuitive explanation of the experiments of quantum mechanics that makes sense. And based on a new postulate, we can actually do that. But you need to know, and you probably do, it's very common knowledge, you need to know the basics of quantum mechanics. So we'll briefly state the old interpretation, and then in contrast, we'll state the new interpretation of quantum mechanics using consciousness that makes sense of it all. So I will start with Isaac Newton. Isaac Newton developed classical or Newtonian mechanics, that is describing physical forms in our universe and how they move through space, amongst a lot of other things. Now, and to do that, Isaac Newton actually had to create some new mathematics called calculus. And he used differential equations to calculate the physical trajectories of objects through space and time. And all the mathematics of Newtonian physics is deterministic. Now we need to know what that means. That means that if you know at any given time, so let's say you have some system, physical system, that could just be a ball or a swing or this, the Earth going around the sun. If you know its position, the positions of all the components of the system, and you also know their velocities, and you know all the forces acting on the system, if you know all that stuff at one particular time, then you can use Newtonian mechanics to work out how the system will be at any other time, later or previous. So Newtonian mechanics is mathematical prophecy, actually, which is an interesting way to think about it. And it's also prophecy that works in both time directions. You can use Newtonian mathematics to calculate the past of a system. That's how we work out how the universe was in the past. We can, Newtonian mechanics or physics is like prophecy into the past. We can look back into the past. We can say approximately what the universe was like in the past, and we can predict the future. Like here's an interesting example. Neil Armstrong or NASA and America get all the credit for landing on the moon, and they deserve a lot of the credit. But probably the lion's share of the credit has to go to Isaac Newton. Isaac Newton did more for humans landing on the moon than any other human, really, because there is no way to work out, or there was no way to work out or let me put it another way, to calculate how to put Neil Armstrong on the moon. The physicists at NASA used exclusively Newtonian mechanics. They used Newton's law of gravity, so they knew the force acting on the rocket, and they used Newton's law of gravity to work out where exactly the moon would be. You need to know exactly where the moon's going to be so you can have the rocket be at the same place at the same time. And you do all that using Newtonian deterministic mathematics, which means, as I say, you can determine things exactly. You can determine the future in principle, according to Newtonian physics. You can determine the future exactly as accurately as you could measure any moment in the past. So your accuracy just depends on how accurately you can make a measurement of the system. Then if you measure all the forces accurately, you can use Newton's mathematics to predict the future definitely. That is, the future is determined definitely using Newtonian mathematical physics. Okay, that's why we call it deterministic. And it's obviously works very well, because it worked well enough to put Neil Armstrong on the moon. So well done to Isaac Newton for that, because he doesn't really get, Newton doesn't need any more credit, does he? He's got enough. Now, so that's deterministic. Now, quantum mechanics comes along and upsets everything totally. Revolution in physics. Why? Because for the first time in, let's say, 300 years, that's a long time, physicists doing only Newtonian physics for 300 years. For the first time in 300 years, physicists have to depart from determinism. Physicists are looking at these quantum experiments, excuse me, and determinism doesn't work. They're trying to use their deterministic methods and they just won't work. So determinism had to be replaced by something. And in particular, it was replaced by probabilism. So that's probability, randomness, chance, entered into physics by way of quantum mechanics. So, and how did Einstein and Niels Bohr and all these people explain this? Well, they said that the basic stuff of our universe, the basic energy and the basic particles, the smallest, most elementary objects in our physical universe, they said were inherently, intrinsically probabilistic. So that's the first interpretation of quantum mechanics, and it was formulated by Niels Bohr primarily, good friend of Einstein's. Einstein hated this interpretation, and of course he said famously, God does not play dice. Niels Bohr replied, because Niels Bohr, was unsatisfied with the Copenhagen interpretation as well, not as much as Einstein, but he wasn't happy with it. He understood why Einstein was unhappy with it. But he said, Einstein, stop telling God what to do. Meaning we just have to describe the universe as best we can. And even if it's weird and unsettling, well, the way it is the way it is. And the way they thought it was irreducibly, intrinsically probabilistic. That is, the results of some experiments can't be determined beforehand, no matter how accurately you measure the initial conditions. You can't predict the final result. What you can do in quantum mechanics is you can identify sets of possible final results, and you can assign a probability to each possible final result. Okay? So in Newtonian mechanics, you can say, okay, the moon weighs this much and it's got this force acting on it. And now we use the maths, and now we can say, okay, in half an hour the moon is going to be exactly here. It's determined. In quantum mechanics, we can't do that. We look at a system and we can say, okay, this is what we can say. The system is either going to end up in this state, or this state. It could be any number of states. Sometimes it's just two states. The example we're going to look at today is just two states. So let's choose two states for the sake of argument. So this physicists of examining a quantum experiment can say, okay, this system is either going to end up in this state or in that state, state A or state B, and then they can assign probabilities. They can say it's going to end up in state A 30% of the time, and it will end up in state B 70% of the time. So if we repeat the experiment 100 times, 30 times it will be in state, approximately 30, not exactly 30 times, but about 30 times it will be in state A, and about 30 times it will be in state B. And there's just no way around this. This is different to flicking a coin. Flicking a coin is different to this, because you think, oh, well, flicking a coin is inherently probabilistic. That's not, according to Newtonian mechanics, that's not true. We could measure the forces on the coin coming from your thumb, with all the currents in the air, and we could measure all these things exactly, or very, very precisely measure all those different parameters, and then we could use deterministic physics to calculate whether the coin would land heads up or heads down. Heads or tails, rather. In quantum mechanics, by principle, you cannot do that. So that's the difference between quantum mechanics and deterministic mechanics. You can only say, oh, okay, it can end up in one of these, any number of states, and we can say how likely each state is relative to each other. And so that's the major difference between deterministic physics and quantum physics. And then there's another major difference, which is, and this is very essential to the point, sorry, just lost my train of thought for a second. What is the other thing that's essential? Oh yeah, so in quantum mechanics, in all the experiments, you're just looking at individual entities. You're looking at a singular, in each experiment, you're looking at a singular definable entity. So you're looking at one particle or one atom or one molecule. And they can choose or select from different possible future states in their experiments. Whereas in macroscopic physics, like with a coin, that's not one physical entity. It's many millions and billions of particles bound together into a bigger entity. And that difference is very important to our, you'll see in a few minutes how that difference is very important to our understanding of quantum mechanics. Okay. So, sorry, get so thirsty. It's very hot where I am. So, yeah, let's examine. It's always good to examine a concrete example. I like to always, ground ourselves in physical reality. There will be no talk of other infinities of universes that have never been measured and dimensions that are too small to ever be measured, because that's not good stuff at all. It's not good physics, philosophically speaking. So yeah, we want to ground ourselves in the physical example. So we're going to choose one famous quantum mechanical experiment, examine it, and compare the two different possible interpretations. And there are many other interpretations of quantum mechanics, but there's still the Copenhagen one is, we would say, the canonical interpretation. As in, if you go and study physics in college, you'll be taught quantum mechanics, and you'll be taught by way of the Copenhagen interpretation. Other interpretations will be mentioned, but the way the course is presented in accredited universities around the world is with the Copenhagen interpretation. Okay. So, the famous experiment we're going to look at is called the Stern-Gerlach experiment. And this experiment concerns electrons. And it concerns electrons moving through a magnetic field. So it turns out that electrons are magnetic particles. That means they have a little, what's known as a magnetic moment. And you can think of that as like a little compass needle that points in a particular direction when it's in a magnetic field. It's called spin. So electrons have spin. Okay? So they're magnetic entities. Okay, and the Stern-Gerlach apparatus is just a magnetic field. It's a scientific experimental apparatus that just generates a magnetic field. So you fire the electrons through the magnetic field to see what happens. And of course, since the electron is a magnetic entity, it's physically affected by the magnetic field. You can send, there are non-magnetic entities, non-magnetic particles, and you can send them through a magnetic field and it won't have any effect. But it will have an effect on the electron. So you send the electron through the magnetic field, and what happens is its spin, its magnetic moment, its little magnet needle always points in one of two directions with respect to the magnetic field. So you can send it into the magnetic field pointing in any direction, and it will always come out the other side pointing in only one of two directions. And those two directions are known as spin up and spin down. And those two directions are, spin up is where the electron has its magnetic moment, its magnetic needle pointing directly in the same direction as the magnetic field. A magnetic field can have a direction. And spin down is when the needle is pointed directly in the opposite direction. So think of the magnetic field like a river, and then a man walks into a river and decides to lie down. He could lie down upstream, or he could lie down downstream in the river. I don't know why he would do that, obviously. Anyway, definitely not important. Now, the thing about our man in the river is that he can lie in any other direction he wants. He can lie with the water parallel to the water or anti-parallel to the water facing the other way, or he can, put himself at an angle with the flow of the river. And basically, the electrons never put themselves at an angle with the flow of the river. If the electron's if the electron is the man, the suicidal man, then he always, lies down in the river, either directly in line with the flow of the river or in exactly the opposite direction. So his head is either upstream or his feet are pointing upstream. So the electron that's how an electron interacts with a magnetic field. Okay. And now, scientists, strange creatures, observe electrons going into and coming out of magnetic fields. They find this interesting, and they observe this, that the electron always aligns in one of these two directions. And then they looked what happens if you change the direction that the electron is in before it enters the magnetic field. Okay? So before it enters the magnetic field, the electron could already be pointing up in the same direction as the field, or it could already be pointing down, or it could be pointing in any other direction before it enters the field. It could be pointing in any direction. And here's what they found. They found that if the electron is what's the opposite of parallel? Perpendicular. If the electron is pointing in a perpendicular direction to the field, exactly perpendicular, then there's a 50-50 split between up and down. So before the electron enters the magnetic field, is halfway between pointing up and pointing down. Okay, we think of up and down as north and south. We can say the electron before it enters the magnetic field is pointing east. So it's exactly between the two possibilities. Then we'll see a 50-50 split. We'll see electrons coming out the other side, and 50% of the time they'll point up, and 50% of the time they'll point down. But it'll be random. It'll be totally random, but it'll be a probability distribution. 50% up, 50% down. Then before the electron enters the field, we could have it pointing at some other direction. So we could have it pointing more up than down. Then we will see that more electrons point up. So let's say we have it pointing very close to up. So it's almost up, but it's just not quite up. Then we'll see, like, for example, we'll see that the electrons come out the other end 90% upwards, but then still 10% of them choose to flip and align themselves the other way and point down. And those percentages depend on the electron's orientation with respect to the magnetic field before it enters. Okay? So I hope you got that clear. So we can't say which way it will align, but we can just give probabilities, and those probabilities depend on its direction before it enters the field. The closer it is to up, the more likely it's to come out up. The closer it is to down, it's more likely it is to come down. But here's the thing. Here's what makes it non-deterministic. An electron could be almost pointing down, but then it can still possibly just flip all the way up. Like, think of our man entering the river. He's already pointing in almost in the down direction with the river, and then he says, actually, you know what? I'm going to lie the other way. I'm going to turn all the way around and lie the other way. But he always lies in one of the two spin up or spin down ways in the river. Okay, I hope you understood that. So there's no way of predicting deterministically. By principle, there's absolutely no way of saying beforehand with certainty which way the electron will point. That's not possible. Well, actually, just technically, the electron could already be pointing exactly. If the electron is already pointing exactly down, then according to the mathematics of quantum mechanics, it will pass through the field and remain pointing down. However, here's another technical point. Because of the uncertainty principle, you can't prepare electrons knowing that they are pointing exactly down in the first place because of the uncertainty principle. So that can't be actually achieved. So there is no way, technically, in principle, of ever predicting beforehand which way an electron will, which way it will orient itself. This is different to deterministic mechanics. In deterministic mechanics, you'd be able to predict. You'd say, oh, look, it's already pointing slightly up, so it will definitely be up. Oh, the electron is already pointing slightly down with respect to the field, so it will definitely come out down. That's how deterministic mechanics will work. So that's the Stern-Gerlach apparatus, is what that experiment is called. So how did Schrödinger and Niels Bohr and Einstein explain what was happening here? Well, they just said that the electron is an intrinsically probabilistic physical entity. It's just intrinsically probabilistic. It has these two sets, these two possibilities of final state. And for some technical language, this is called the collapse of the wave function, is when the electron actually chooses. So all quantum mechanics experiments will have possible final states, and then the actual selection is called the collapse of the wave function. You don't really, it's quite famous language now, but you don't really need to know these things, but that's just a technical terminology, the collapse of the wave function. So they said that the collapse of the wave function was a inherently, intrinsically probabilistic act. They said that the basic stuff of our universe is just intrinsically probabilistic. We are in a probabilistic universe. And to repeat, as you know, Einstein famously hated this and said it was wrong, and of course, Einstein's never wrong. You know, there's that story about, or that phrase, or whatever about Einstein, even when he was, I forget who said it, but even when he was wrong, he was right. Yeah, so they say that, so the canonical, the standard, the accepted, or most accepted interpretation of quantum mechanics, known as the Copenhagen interpretation, says that the collapse of the wave function is intrinsically probabilistic, so that the basic energy and particles of our universe are intrinsically random. Now again, yeah, it's very, that's not a good explanation. That's not good. It's not a good interpretation of quantum mechanics. Why? Well, because we are made of nothing but these quantum particles. And another thing, just to be more clear, their interpretation of quantum mechanics was that basic energy and particles are non-conscious and intrinsically probabilistic. And this is not a good explanation for a lot of reasons, but the main reason is, well, we're made of nothing but these particles, and we are conscious, and we also, our experience of consciousness is not probabilistic. That is, it doesn't ever feel to you like there's just some random chance. You know, let me give you an example. If I offer you Coke and Pepsi, and you make it, and you know, which do you prefer? You probably prefer. I prefer Coke. I think most people prefer Coke. I think it's the most popular drink. I think that's safe to say. So, but I could say to you, hey, Pepsi or Coke, and you'll say whichever is your favorite. That won't feel like it was intrinsically probabilistic. That will feel like you made a conscious, free choice between two possible sets, between a set of two possible outcomes, receiving a Coke or receiving a Pepsi. So it doesn't, you know, our experience of being formed out of these particles doesn't coincide with probabilism, and it doesn't coincide with particles being non-conscious. What it does, what our experience of consciousness is, one, that we're conscious. Your conscious experience is that of being conscious, and it's also your entire life you've had conscious experience of making conscious choices from limited sets. You do this all the time. So, based on our new fundamental postulate, we postulate our new fundamental postulate, and then we use it to reinterpret quantum mechanics in a way that makes much more sense. And it's very simple. It's very simple, but it's revolutionary. Now, our fundamental postulate is that all energy is intrinsically conscious. That means that when this intrinsically conscious energy makes particles out of itself, which is what the universe has done, the energy created in the Big Bang, subsequent to that Big Bang, created particles out of itself, such as electrons. That's undeniable, because unless you're saying electrons don't exist. And if the energy is conscious, then so are the particles. So now we look at quantum mechanics and we interpret it based on the postulate that all the quantum entities being studied and examined are conscious entities. Okay, so now we look at our Stern-Gerlach. So now, and in technical language, we say that where Niels Bohr said that. I'm imagining a comment referencing Niels Bohr and calling me a Bohr now. I'm kind of paranoid, haven't I? Anyway. Well, you know, some people are interested in this stuff. I am, obviously. What was I saying now? Oh yeah, Niels Bohr said that the collapse of the wave function is an intrinsically probabilistic act with nothing to do with consciousness, and we're changing that to the collapse of the wave function is a conscious act. So now the electron is a conscious entity, and now we're saying that when it selects between spin up and spin down, that's a conscious choice it makes. Now, let's be very clear. When we say an electron is a conscious entity, we do not mean that it has any sort of personality or is like, woo, I'm flying through space, I'm an electron, ooh. No, obviously, an electron is an exceedingly simple formation of consciousness. Very simple. And therefore, we can safely assume that its conscious experience is proportionally simple. So it has no linguistic abilities, because we know from studying life on Earth that linguistic abilities take large brains. We're the only animals with linguistic ability. That doesn't mean that other animals aren't conscious. Of course, chimpanzees are conscious, but they don't have the complexity in the configuration of their brains to be able to speak. So as we look back in life, we see that consciousness gets simpler. Like we know that chimpanzees have simpler conscious lives than we do, and we know that an amoeba has a simpler conscious life than a chimpanzee. So an electron has an even simpler conscious life still. And then an electron is an elementary particle, so it has the most elementary consciousness. So when we say an electron is conscious, we mean it has conscious experience of, for example, a force acting on it. You know, when a force is acting on you, you can feel it consciously. You know what it feels like when you take off in a plane, the force of the seat pushing pushing into your back as you accelerate. You know how that feels. That's the feeling of a force. An electron, if it experiences a force, which electrons do experience as forces, it will consciously perceive the acceleration, just like you do on a plane. But you're a more complex configuration of energy. So you're on the plane, you can feel that conscious force, and at the same time you can watch a movie and think about the movie. That's because you're much more complex than an electron. An electron just has very basic consciousness of forces and fields and accelerations and electric charge. It's an electric particle, so consciously sense electric fields, just like you consciously feel gravitational fields. Okay, so yes, the electron is a conscious entity. And so are all quantum entities in quantum experiments. So that's the fundamental postulate for quantum mechanics. The quantum entities are intrinsically conscious entities, just like you're intrinsically conscious. So then we state the two most fundamental properties of all conscious entities that have ever been studied. And this is how we define if something is conscious, really. But this is not the scientific definition of consciousness. The scientific definition of consciousness, I think I'm going to do in the technical scientific definition of consciousness, I think I'll do in the next lecture, 3. Um, what was I saying? An electron is conscious. I've totally gone blank now. Where was I? Bear with me, please. Maybe I should eat a banana. Oh, simpler forms, yeah. So the electron is very simple, so it has very simple consciousness. And see, we're saying all energy is conscious. So that means all physical processes and all physical interactions are also conscious interactions. And that makes a lot of sense. If you touch a table, or touch your leg, or touch your mattress, that's a physical process, and it's a physical interaction between the physical stuff of your hand and the physical stuff of your bed. And that physical interaction, that physical process gives rise to the specific conscious experience. So that's an example from your own life where a physical process is also a conscious process. So the electron is a physical entity, and it's also a magnetic entity. So given that it's a magnetic entity, it has physical interaction with magnetic fields. And all physical interactions are also conscious interactions. And all physical processes are also conscious processes. So its physical interaction with the magnetic field is also a conscious interaction between it and the magnetic field. So in other words, that's what I was saying. Sorry. I was saying about the two basic characteristics of all conscious entities are some perception of your local environment. So that's important. Consciousness is a local phenomenon. So you have consciousness, and you have consciousness connected to and consciousness of your surrounding universe, but your consciousness is only of your local surrounding universe. That is, you can see and feel and exist within your or have conscious experience, of your local surrounding universe, say the room that you're in, but you don't have conscious experience of the other side of the universe. So consciousness is local, and our conscious entities have conscious perception of their local surrounding universe, and conscious entities have the conscious ability. So now, this is quite important to get clear in your mind. All conscious entities have the conscious ability to select from limited sets of future possibilities to instantiate. So, what does that mean? Well, you're watching or listening to a YouTube video now. You have perception of your local surrounding universe, so the room that you're in, and you have conscious perception of whatever screen you're using to listen to this, and then there's the dislike and the like thumb buttons, and they are two possible future state. You clicking on the like or the dislike are two possible future states that you can instantiate. Or there's a third possibility, you don't click on either. So you have a set of possible future states or possible future actions. Clicking like, clicking dislike, or not clicking at all. And you have the conscious ability to select from that limited set of future possibilities. Okay. So we're saying that all identifiable conscious entities have those two properties: perception of their local universe, conscious perception of their local universe, as well as the conscious ability to choose from limited sets of future states and future actions. Okay, so let's look at the Stern-Gerlach. The electron is a magnetic entity. It enters an magnetic field. Because it's a magnetic field, because it's a magnetic entity, being in a magnetic field is a physical process, a distinct physical process, and therefore a distinct conscious experience. So an electron has a different conscious experience when it's in free space than when it's in a magnetic field. They are different conscious experiences. You can understand this. Remember, you're made of nothing but particles like electrons, protons, and neutrons. You're in a gravitational field, and being in a gravitational field is a very different conscious experience than being in free space. You can see the astronauts who have gone into space and experienced zero-G can tell you it's a very, very different conscious experience. It's one you eventually get used to, but at first it's very different. You definitely know the difference between being in a gravitational field and not being in a gravitational field. I mean, a field as strong as the Earth's. Because technically you're always in a gravitational field, but if you're in free space, well, let's not get into. We don't need to talk about gravitational fields at the moment. Suffice it to say that there's a difference in conscious experience of being in a gravitational field and not being in a gravitational field. And we are saying the same thing for an electron. As a magnetic entity, there's a difference in conscious experience from being in free space, out of any magnetic field, than being within a magnetic field. Okay. So, the electron enters the magnetic field and has a difference in conscious experience, a change in its conscious experience, and this change in conscious experience is such that the electron then always consciously chooses to align its magnetic moment, either spin up or spin down with the field. So now we have explained that experiment using consciousness as opposed to probabilism. And we can explain all quantum experiments in this way, because all quantum experiments involve a wave function and involve the collapse of a wave function, and the collapse of a wave function is always where the system selects from a limited set of possible future states to instantiate. That's all quantum experiments involve, that collapse of the wave function. And so now we're just saying that this collapse is always a conscious choice made by the quantum entity in question, where the particular set of possible future states is defined by the experimental apparatus, such as the Stern-Gerlach experiment. Okay, so I don't want to go into too much detail here in quantum mechanics. Why? Because in my other audio essay, which is an hour and a half long, I go through 4 different experiments, and I showed that this is the correct interpretation of quantum mechanics using consciousness. So I just want to do one experiment here, just to explain how we can get the correct interpretation of quantum mechanics using consciousness, and then I want to move on to other things. So if you're interested in a more detailed explanation of quantum mechanics, and particularly in that longer essay there's an interpretation of the very famous two-slit experiment from quantum mechanics, then I highly recommend checking out that longer lecture. So, okay. So now we've changed things. So the electron is a conscious entity. It perceives the surrounding magnetic field, and then it chooses between spin up and spin down. And now we get a very natural, and this is totally scientific. Niels Bohr said the stuff is just intrinsically probabilistic. Well, and that's been accepted as science for 100 years. If you could say that, if you can say that matter is intrinsically probabilistic, you can say it's intrinsically not intrinsically consciousness, intrinsically conscious. Okay. So, and then we can speculate a little more, and we can even come up with an even more intuitive or a fuller or a richer interpretation of this experiment. Because, as you know, like being physical processes have corresponding conscious experiences associated with them. So you're in the Earth's gravitational field at the moment, and you have conscious experience of it. You can feel that weight. You would certainly notice if the gravitational field suddenly switched off, then you would certainly notice not feeling that weight anymore. And if you were on a planet with a much stronger gravitational field, you'd feel a whole lot more force. And that force could get so much that it could start to crush you. And you would definitely notice that consciously. If you're on a much denser planet with a much stronger gravitational field, such you would be crushed, and you would definitely feel it consciously. It'd be, well, for as long as you survived. And yes, so based on our physical circumstances, there are different conscious experiences. And some conscious experiences are more pleasant than others. That can't really be denied. We are all in the field, in the radiation field of the sun. And being in the sun is pleasant from this distance. But if we were much closer to the sun, we'd be in a much denser part of the radiation field, and we'd be burnt. So we're at a nice distance from the sun, okay, in terms of the radiation field. So we like to stay at this distance. We're already positioned at an appropriate distance from the sun. If we were much closer to the sun, like if I could take you much closer to the sun, you'd very quickly want to move back away from the sun because it's far too hot. My point being is that when you're in some field, there could be a place, preferable places to be. Some places to be are much more pleasant than others. And so your orientation within physical fields can be more pleasant or less pleasant, depending on how you orient yourself. So we can say with the electron in the magnetic field that aligning its magnetic moment exactly upstream with the magnetic field or exactly downstream with the magnetic field are the two most pleasant conscious experiences that the electron can experience while in a magnetic field. Or maybe not the most pleasant, maybe the least unpleasant. And then we can say we know from our study of all conscious life, and you know yourself, that any conscious entity always tries to maximize pleasantness, maximize pleasant experience, and minimize unpleasant experience, such as pain. So then we can say, then we say that the reason there's a 50-50 split between spin up and spin down is because those two positions with the electron needle pointing with the stream or in exactly the opposite direction of the stream are the two most comfortable or least unpleasant states that the electron can be in with a magnetic field. And of course, all conscious entities, no matter how simple they are or how stupid they are, all conscious entities try to avoid pain, discomfort, and try to maximize pleasure. All of us try to maximize physical comfort. You know that from your own life, and you're made of nothing but electrons, protons, and neutrons. So the theory is that they also try and maximize comfort and minimize uncomfort. So now we have a reason why the electron always aligns in one of these two directions, which is quite interesting. Okay, let me check the time now. Oh, 49, okay. 49 minutes. So, yeah, I think that's enough of quantum mechanics. Yeah, if you'd like more details on quantum mechanics, on Reddit I've written several essays on quantum mechanics. And yeah, there's the longer audio essay that I've mentioned, where I explain the Stern-Gerlach experiment, as I've just explained it, and I explain 3 other famous quantum mechanics experiments. Now you can see how we have an intuitive way of understanding the experiments of quantum mechanics, but it involves consciousness. It involves assuming that these particles are conscious. But that makes a lot of sense, because that's all we're made of, and throughout your entire body you have conscious experience. And you spend all day choosing between limited sets of possible actions to take, just like electrons. So that's a good, scientific, consistent way of explaining all of quantum mechanics. Any experiment with a collapse of a wave function. Okay, so another quick point based on a point about the mathematics of quantum mechanics. The mathematics of quantum mechanics is probabilistic. You get probability distributions for the results of experiments. Now you might say, hey, well, if the mathematics of quantum mechanics is probabilistic, then surely the quantum entities are probabilistic. But no, that's not a reasonable conclusion to jump to. Why? Because as we know from the sciences of economics and psychology, soft sciences of economics and psychology, when you are looking at individual conscious entities making individual conscious choices, you have to use probabilistic maths. You have to use probability distributions. So economics and psychology, which deals with large numbers of humans making choices, specific, well-defined choices from limited sets of possibilities, you are also forced to use probabilistic mathematics. So that is, probabilistic mathematics can be used to describe inherently probabilistic things, but it is also the mathematics that we use to describe individual conscious entities making individual conscious choices. So the fact that the mathematics of quantum mechanics is exactly the same, this is very interesting, the mathematics of quantum mechanics is exactly the same as the mathematics of psychology and economics, where you have large numbers of individuals. So, for example, you take some boy and you observe him at some time. You can't determine beforehand if, for example, he will get married before he's 40. That can't be determined beforehand. But you can say he's a man from, you can observe a lot about him. You can say he's a boy from wherever, and boys from that particular part of the world, there's a 70% chance that they will marry, have married at least once before they're 40. Okay, so then you can't determine the future of the boy's life. It's not deterministic, it's probabilistic. Why? Because he's a conscious entity that can choose, and all our choices are free choices. Like, according to my theory, you do have free will, but you have limited free will. You can only choose between limited sets of possible future actions and future states, and you have to be able to imagine those possible future actions and future states. And that's proportional. Your ability to imagine future states depends on your level of intelligence. So yeah, we believe that other humans are conscious, and when we study other humans making individual choices, we have to use probabilistic maths. And then we go to quantum mechanics, where we're studying individual particles and individual atoms and molecules. That's very important. that distinction between microscopic quantum mechanics and macroscopic physics, where a macroscopic object isn't an individual physical entity. It's many millions or billions of individual conscious entities bound together. And so there's no individual, so if you throw a rock, there's no individual consciousness making an individual choice. All the individual atoms of the rock are bound together and they can't free themselves. And you throwing the rock imparts a large force on the rock that the particles can't resist. No individual particle is making choices for the whole rock. They're all just bound together and vibrating together. Each individual particle in the rock is just making whatever momentary conscious choices it makes in terms of, vibrating and changing energy levels and such. So that's the difference between microscopic quantum mechanics and macroscopic deterministic mechanics. Like, here's a very good analogy that explains it quite nicely. You have one person and you're observing them climbing up a hill. On the top of a hill. You have one person on the top of a hill, okay, and he's walking around the edge of the hill, and you're watching him, and he's like, oh, he could fall down there, but it's not too steep. So you're like, no, he'll be fine. He's on the top of the hill. He's walking around the top of the hill, and he can walk to the edge and walk down a little bit. So he can walk down to the middle of the hill. I'm reminded of that nursery rhyme now. What is it? He marched him up to the top of the hill and he marched him down again. Grand Old Duke of York. There you go. So we've got thought experiments with the Grand Old Duke of York. So he's on top of the hill. He can go to the middle of the hill. He's at the middle of the hill. He doesn't have to continue following the force of gravity downwards. He can overcome the force of gravity using the strength in his legs and walk back up the hill. And you can't say what he's going to do, because he can walk down to the middle of the hill, stay there for a while, and then continue downwards, or maybe he'll say, oh, I left my sunglasses on the top of the hill, and now he changes his mind and he's going back up the hill. And you can see how it's unpredictable. Why? Because there's one conscious entity making the choices, one conscious entity in charge of what's going on. Now imagine the scenario, but instead of the Grand Old Duke of York, it's him and all his friends, him and 50 friends, okay, that's too many, him and 10 friends, and they're all tied together with ropes. So their arms are all bound to, they're each bound to their nearest neighbours by ropes, so their hands, don't know who's done this to them, or why they've done it, well, for this experiment, I suppose. I've done it to them for this experiment. I've tied their hands and feet together with rope and their nearest neighbours, and I've made a kind of macroscopic object out of, or, even bigger object out of all these separate, individually conscious humans. Okay, so they're all bound together. Now you see, if this bound object, now all their individual conscious wills are very much restricted. Each person tied within this, human molecule is constrained. His free will is less free. So when I say we have free will, I'm saying limited free will, not total free will. You can't do whatever you want. You can only do what you're physically capable of doing, but you do freely choose what to do. But the universe can put restraints on you such that it limits the set of things that you can choose to do. So at the moment you can get up and walk around your room, but I could come and tie you to your chair, and then I would put a constraint on you and I would limit your free will. You'd still be able to choose to blink, turn your head, and within your mind you'd still be free to choose to imagine whatever you wanted, but you won't be able to get up and walk around anymore. So you have limited free will. So back to this human molecule. The Grand Old Duke of York and his friends are tied together, and they're on the top of the hill. Now if they get too close to the edge of the hill, so now 5 people are kind of leaning over the edge of the hill, and that 5 people are feeling the weight pulling them down, once one falls, there's some point of steepness to where once one of them falls, he will pull all the rest of them down. They'll start falling. They'll reach a tipping point where once they start falling, they can't stop falling, because of the way that they're tied together and the lack of coherence of their bonding means that they can't consciously resist gravity. So once they start, it's not like the original example where he can walk down and then walk back up. No, if they start going down, then they're going down. And that's the essential, this is very, very important analogy to understand, because for a long time, scientists have been trying to understand what's the essential difference between quantum mechanics and deterministic mechanics. And this analogy is the essential difference between quantum mechanics and deterministic mechanics. In quantum mechanics, you have an individual that can make that's making all the conscious choices for itself. And therefore, we have to use probabilistic maths. We can only say, there's a probability it will do this, or probability it will do that. But the entity in question has to decide itself, and it has free will. So you can't predict beforehand what it will choose. If we could predict beforehand what it will choose, then that's not free will. So, but then when it's bound into a macroscopic object, then we can determine what will happen. We can say then it becomes deterministic. And if we push the human molecule beyond a certain point on the hill, once it starts falling, it will deterministically fall all the way down the hill, and we can say where it will wind up, because none of the individual members of the bigger object is in control of what's happening. They're just all succumbing to a force that they're not coherently connected together enough to oppose. So yeah, that's quite important, actually. The essential difference between quantum mechanics and macroscopic physics. Oh boy. Tired. So I hope you understood that. I've kept both lectures to an hour, so that's okay, not bad. I hope you understand. If you have any questions, feel free to ask. I love getting questions and explaining these things. That's how the theory develops, and I'd love help in developing the theory. I mean, that's the thing about this theory is it's teachable. There's been no theory of consciousness before that's actually teachable. I can teach you the basic principles of the physics of consciousness, and then you can use them to analyze consciousness yourself. And you can teach it to other people. You can start doing conscious physics yourself. And listen, this is a new branch of physics. So, if you want your name attached to a theory or something like that, study these principles carefully and get to work. Get your name attached to something. Remember, Isaac Newton developed the principles, but then since Isaac Newton, there were hundreds of famous classical mechanics after Isaac Newton who have theories attached to the name. Hamilton, Lagrange, so many, Laplace, whatever. Hundreds, literally. But yeah, it does mean having an open mind and viewing the universe in a way you've never viewed it before, because it means you're surrounded by consciousness and you're made out of consciousness. But you don't have to worry about, your chair's not, whilst your chair isn't a singular consciousness. Your chair is just made of many, many billions of individual conscious electrons, protons, and neutrons. And those electrons, protons, and neutrons are conscious, but in a way that, from a human perspective, doesn't really mean very much. They just feel pressure and heat. There's no personality, there's no linguistic ability, there's no capacity to love, so you don't have to worry about these things being conscious. They just have bare basic feelings, which, if that's all that's there, we know there's less importance to things like that. Humans and animals and plants are much more complex things and have much more complex conscious sensations and feelings and experiences, and that's why they're much more precious. And that's why naturally we value humans the most, and then we value animals next to humans, and we value plants next. But stones and chairs and things like that don't mean anything. Why? Because breaking a stone doesn't have any meaningful effect on the existence of the atoms that make up that stone, because they're all just individuals, and they're all very basic and don't have refined feelings that you need to be careful of. So now we have seen, but this does all require an open mind. But this universe requires an open mind. You're flying through space on a ball of rock, and literally a ball of rock. There are people facing the other, hanging off the other side of it, pointing in the opposite direction. You're being pulled by this weird invisible force to the center of this flying rock that's going at incredible speed around it. A ball of fire that's impossibly large. The sun is too large to imagine. Like, the Earth is big. But I remember reading in physics class, there was a poster in my physics class that said that the mass of the sun takes up 99.9% of the mass of the solar system. So the sun really is unthinkably big. So you're on a ball of rock flying around a ball of sun that's really big. So my point being, any understanding of this universe, any understanding of this situation that you're in and that I'm in, requires an open mind. Like, all this energy was crammed into one single point and it exploded and atoms made in billions of years. And then with relativity, Einstein showed that time is different for everyone and everything, and that lengths can change depending on how fast you're going. So the thing about the truth about our universe is shocking and amazing. But now you're starting to see a picture of a conscious universe, which is really quite an amazing picture to see, or it has been for me at least. That we've got here from the Big Bang through a vast number of conscious choices based on this conscious universe trying to find the most pleasant path, or the most pleasant way of being, the most pleasant conscious way of being. And here on Earth, for humans, that's resulted in basically the concept of love and things like that. Anyway, kind of rambling a little bit again. That's that. So what have we done now? Let's add some more check marks to our theory. Let's check our check marks. We have a scientific fundamental postulate for consciousness, which is that all the energy created in the Big Bang was and is conscious intrinsically. This solves the hard problem of consciousness. Check. Now we've just shown that the same postulate can be used to give a logical, intuitive interpretation of the experiments of quantum mechanics. Check. That's a big check. No other theory has that. And this theory of consciousness, this interpretation of quantum mechanics makes sense, aligns is the right word, aligns with our own experience of human consciousness. Because you are in the universe. Like, the universe, your surrounding universe is like an experimental apparatus that you're surrounded by. It constrains you. The different forces and things that are acting on you and surrounding you, like the gravitational field of the Earth acting on you. You have conscious perception of these things, and you can make free choice between different possibilities depending on the nature of the universe surrounding you. Okay, so our interpretation of quantum mechanics makes sense of the experiments, and it aligns with our own daily experience of limited free will. So yeah, so do you have free will? Yes. But it needs to be qualified a little bit. Because there's a great debate about free will, and it's a very important one. Yes, you do have free will, but it's limited, and it's limited by the physics of the surrounding universe. Okay, that's definitely enough now. So I hope I made everything clear. So in the next lecture, I think I'm going to do actually the next lecture. Next lecture, I think, will be different applications of this theory. So we're trying to build a theory of consciousness. We want it to explain as much as possible. The more it can explain, the more we can trust it. If we look at this phenomenon and this phenomenon, and we keep on being able to use my theory to make a sensible description of it and theory of it, then the more we can trust my theory. So I think in the next lecture, what I'm going to do is explain how my theory can be used to come up with a theory of human conscious physiology. Okay, so yeah, in the next lecture we'll talk about, human visual perception, hearing, taste, hunger, and how we can make deductions about other conscious entities and what consciousness they experience. I think that'll be good for the next lecture. Then, after that, we will have a lecture on the technical, scientific definition of consciousness. Yeah, so as I said, people might expect that to come first, but I don't think definitions actually do come first. First you have to observe, then you make the definition. So we've made lots of observations of our universe so far, including, well, you've made observations of your own consciousness, and we've made scientific observations of the universe, and such as quantum mechanics. So we've looked at all that, and it's our inspection of all these things that will help us technically define consciousness. So yeah, that will be lecture 4, where we give the technical scientific definition of consciousness. And I cannot tell you how tired I am of the word consciousness, because I have been using it a lot over the past few years. Okay. So, take care, all the best. Bye-bye.